Oh, welcome back, guys. Okay, so today we are going to continue for the introduction to machine learning from Kaggle. I think if you've been following my YouTube channel on data science, I think it's on part 5. So today should be part 6. I think the last time it was we're trying to understand underfitting and overfitting. And then we already did the exercise. So there's some things that I want to add um, after listening to other or reading other materials about underfitting and overfitting. So I mentioned about so basically we want to try to build a general model and a model if you think about the from mathematical background you can think of it as a mathematical functions which has number of parameters or we call it hyperparameters, right? So in general, I would say the more number of hyperparameters or number of parameters in that mathematical function, the more complicated the function is, right? So in a way, you can also call it uh, um, say it as overfitting, right? It's not a must, but it's kind of like in general rule of thumb. But so on the opposite way, if you have like a less number of parameters, then you can say it's kind of underfitting. That's like the easiest, the simplest way. I'm like overgeneralizing here, like you know. But you can also say overfitting means that if there's a particular parameters that during the training process, remember the way to make it general if you remember from our previous session, is we split the model into two. Basically, there are the training data and the test data. The idea is we want to train the model using the training data instead of the whole bunch of data. So after that, we can a way to test the model using the split data, which we call the testing data, right? So for example, and we are using home pricing. So if you can think of like, for example, what's the like that the one that makes sense that the features that determines the price of the home. For example, the number of how big is the home, right? The number of square feet, the number of bedroom, number of toilet, probably whether there's a good public school, and probably there's a you can think of say the number of trees. Who knows, right? But so when you train the model, and then it turns out the number of trees is particularly related to or causing the fluctuation of the home prices, right, on the training data. But when you use that the same model that you already trained using the training data, and one of the features is trees, the number of trees, it turns out on the test data, it turns out that the number of trips actually it doesn't correlate or it doesn't make any impact at all whatsoever. So you can say that the model is kind of overfits because it's just only overfit on the training. Remember, overfit means like um, it's like when you're fitting a shirt, right? And your shirt is just fits just for you, it's just for that particular you. In that sense, that you can replace it on for that particular data, right? But when you change the you give it your shirt to other person, it doesn't fit at all, right? So so in a way you want to make your kind of your shirt to be more like general. In a way you want to make it a bit kind of loose, not to overfit to your contour, right? So when you kind of share it or when you want to, it's time to donate it to other people, you go to Goodwill, and then you can like other people that are probably not as fit as you or not as has the same body curvature like you, they can still use your shirt, right? So it's not wasted kind of. So in a way that the parameters it's not so just fitting in your curve, right? Um, so that's the idea. So today we're going to this I think part number 6 or 7. So we're talking about random forests. So we've been using decision tree, right? I think random forest is part of that decision tree algorithm is just slightly more complicated or more sophisticated. So we're gonna take a look at that. Um, so we can see here, right, decision tree, leave you with a difficult decision, blah, 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 a deep tree with lots of leaf with overfit because each prediction is coming from historical data from only a few houses at its leaf. Okay, so um, we're just gonna, so here's conclusion. There is likely room for further improvement, but this is a big improvement over the best decision tree error. Okay, so basically you are, let me see. So many models have clever ideas that can lead to better performance, right? We look at the random forest as an example, right? So it says, but a shallow tree with few leaves will perform poorly because it fails to capture as many distinction in the raw data. So will perform poorly because it only have few leaves, which means only have few parameters, right? Which means is underfit, right? It's too loose. When you're wearing a shirt, your shirt is too loose, so it's like underfitting instead of overfitting, right? Um, and this, we are using random forest to kind of trying to mitigate this problem, basically to for better performance, basically trying to make it more generalized, the model. So the random forest uses many trees and it makes a prediction by averaging the predictions of each component tree. So basically it has many decision trees model, and then it uses all each of these models of decision trees, and then after that you get the result of for each of those trees, and then you average those trees, right? So you get a more kind of generalized kind of form. In general, has much better predictive accuracy than a single decision tree, right? Because it uses many. It works well with default parameters. If you keep modeling, you can learn more models with even better performance. But many of those are sensitive for getting the right parameters, right? So I know why this is called random forest, right? So you can think of a forest is a compilation of a trees, right? That's what it is. In real life, forest means there's many trees. So um, because in this algorithm, you're using not just one tree, but many trees, many decision trees. I think it's random because after you're using many decision trees, you are kind of average those, right, from those trees, and get the best kind of get the best result. So you're using the code to load the data a few times. At the end of data loading, we have the following variables. So again, we divided the code into basically two categories, the training and for the test, or you can say the training and for the validation, right? And for each the category you want to is divided with two basically, which one is the because machine learning is about giving inputs, right? The X, and you want to is this is about supervised, is under the category of supervised learning. I don't know if you heard about that, but in the area of machine learning, basically, I think there are three category. I think there's supervised learning, unsupervised, and I think the other one is reinforcement learning. I think, and I think that's the kind of uh, and supervised is, I think, is the most common and the most used, and probably is the most practical, the one that we've been using on our everyday life. Like for example, I think the face recognition algorithm that you use in our iPhone is something is using a supervised learning method, because you have to teach it and then you have to know which one is the input, which one is the output, right? So off tangent over there. So over here is basically we are dividing into X and Y, right? The input and the output, and each of the X and Y we're dividing into two again, is split into two because we want to make be able to test again after we train. So we divide by train and we call it this validation, right? And then we built a random forest model similarly to how we built a decision tree in scikit-learn. So we are using a random forest regressor class instead of decision tree regressor. So what you want to do is just you go to sklearn.ensemble and then you import this guy and then you go to the metrics to find out um, how accurate, right, it's your model is by importing this guy, this algorithm mean absolute error, right? Uh, Basically, you are comparing the predicted output with the actual output, right? So you're like subtracting it, and then you get the absolute, and then you average it all across the board, right? Um, and then we are going to put it inside the pointer, right? Forest model. We want it to be reproducible, right? And then we start to train it. So we call dot fit, right? We put in the parameters, which is the x and the y, right? To train, remember, to train something, you need an input and you need an output. You want because this is a supervised learning. So imagine in supervised learning, imagine you are a teacher. What does the teacher do? The teacher give example to the students, which is the model, and the teacher also give the answer, kind of, right? Because this is called supervised. So the teacher has to give the answer. In unsupervised learning, the teacher doesn't need to give the answer, right? So this is supervised, you need to give the answer. So you need the input, you need to give an example to your students, to your model, and you need to give the correct output to the model. So you need the X and you need the Y, right? Over here, the X and you need the Y. Two parameters. And because you want to be able to test again your model, you want it to be generalized, not overfit or underfit, then you want to break down the data into two, training and test, or training or validation, right? So once we train it, then we got the model, we got the hyperparameters already ready, and we want to call the prediction, right? Using the model. So we call it dot predict, and then when we want to predict, then we want to use the testing data, right? We want to use the testing data. What kind of parameter do we call? Because we want to predict, because we want to predict the output, right? So we need to give the input. So we need the X, but we need the validation X, or the testing data X, right? So this is what Y is validation X. And then after that, we are just going to calculate the difference between the two. So we call this algorithm called mean absolute error. And what are the parameters? The parameters are the actual prediction, which is also the actual value. So it's not the actual prediction. There's no such thing. The actual prediction is this one, right? The malprets, this one, and then the actual value, right? So this one you can like just like interchange it, like which one is the front, which one is the back. It shouldn't matter, and then you print it, and then this is what you get. So this is kind of the how big is the error is. Okay. So conclusion: there is likely room for further improvement, but this is a big improvement over the best decision tree error. So we have 250,000. Over here we have only 202. So if you go back, let's say over here, let's see. No. And we go back to the courses, and then I forgot already the 250,000. This one. Yeah, yeah. So it's more than 260. Yeah, 264,000. So over here we only got about 200,000, right? So that's good. So there are parameters which allow you to change the performance of the random forest much as we change the maximum depth of the single decision tree. Okay. But one of the best features of random forest model is that they generally work reasonably even without this tuning. Okay. So you don't have to tune it. This is kind of like the default already, the default parameters. And then we'll soon learn about XG boost model. This is kind of like one of the most kind of popular and in machine learning algorithm, probably the most widely used. Even I can like commit that a friend of mine who works with Ella Lilly, it he actually likes to use this XGBoost model to for prediction. So it's really being used in a practical world, not just in in a theoretical sense, in just not in a practice sense, because you're in Coursera or you just like in YouTube or whatever, right? But it's really being used a lot um, in a practical world, not just in a probably in a Kaggle world. Uh, and many people love to use this because it's just it gives like a very kind of like a nice prediction, good enough. You don't have to like tune it a lot, probably. You don't have to work hard at it, and quite acceptable even to the business world. They can accept it. Anyway, so um, which provides better performance when tuned well with the right parameters, but which requires some skill to get the right amount. Okay. Okay, so now we are going to open this to a new tab. We are going to do the exercise. All right, let's see, it works. Okay, let's see, version. Should I turn the GPU? Uh, the GPU is still off. I think you can just leave it off. It's fine. Okay, so we are going to import all of this thing, right? This is the previous one, right? So we are importing this. We are importing pandas. Pandas is for data frame. Sorry, but those loud things. I'm actually here on a vacation here with my family, so my kids they're having fun, and when they're having fun, sometimes they just keep on shouting. So ignore that. And then we also import this algorithm to test the within train and validation, train or test. We imported decision tree regressor. We are pointing up, set up a pointer to the training data for the home data, but over here it's not here. Home data for ML course. It's not here. Yeah. Anyway, so it should be like probably it's like hidden somewhere. Yeah, this is the one I don't understand like the um kind of the structure of how Kaggle is being. So probably Rachel or Dan Beckers, probably if you heard this video, um, yeah, I'm trying to answer his question, but I'm not sure because some of the data is or this is just for practice purpose. It's not feasible here. But anyway, um, and then you have to put this dot dot. This is really important. Like there's one time I spent a lot of time not putting this one and just putting like slash input and this and it doesn't work. Okay, you have to put this dot dot. Anyway, um, so and then you want to read it, so you use read those dot read CSV from the PD, read it, and then you put it on the Y pointer, the sell price, right? And then you create an input using the features that you already selected. This one has 7 features. I'm just gonna minimize this, right? Lot area, your build, first floor, second floor, full bath, bedroom, and total room above. Wait, wait. Shh, shh, shh. Sorry for about that. This is my family. They're just so crazy. Um, and and the so okay, where am I? I lost my train of thoughts. So the X is the home data features, and then we're gonna split into validation and training. So we set up a number of 4 pointers, right? Train X, train Y, validation Y, and then we call that algorithm. And then we put the parameters. What parameters we are inputting? Of course, it's the X, the whole, the whole, not the whole, the input data that you already pre-selected, the features, these 7 features, and also the pre-selected output. In this case, is the sale price, right? The sale price, and then you want it to be reproducible, right? So you put random state equals to 1, right? Um, and then after that, we specify the model. So we call decision tree regressor. Again, it has to be, I'm not sure why this has to be reproducible. Like, because is there, oh, probably when you call this algorithm, it has a specific default parameters, because this is basically you're calling a function, right? So let's say you're calling like y equals to, I don't know, 5x plus, I don't know, 5x plus 2 or 5x plus, 3. So you want that 5 and 3 should like always, every time you call that function, is always you're calling the same specific function instead of one time. If you don't specify this, I think it's going to call y equals to 5x plus 3 one time, and then you call it again, it's going to call y equals to 6x plus 2, and then you call it again, is going to call like y equals to 10x plus 1. So it's going to be keep on giving you different kind of um, parameters to start with every time. Okay, so I understand that. And then after you call every the data you call, the algorithm you already called, and then now you start to train, right? So you have the model, which is the algorithm. You have the data, and then you're gonna train that model. So you call dot fit using that model that you already call, and then you want to put the pointer, right? Which is 2 pointers. Remember, you're becoming a teacher, so you need to put what to your students. You have to put uh, the examples. You have to give a lot of examples to your students, right? And you have to give the answer, because this is supervised learning. Supervised means you have to give the answer, right? That's just what supervised means. You have to tell it to your students that, okay, for this particular problem, this is the answer. For this particular problem, this is the answer. For this particular problem, this is the answer. That's called supervise. Um, After you train the model, then you want to know how good, right? That makes sense, right? So you already kind of test your students with a lot of example, with a lot of answers, and now you want to test your students whether your students really learn what you have teach them, right? So in order for them to test your students, you call dot predict, right? Dot predict to that model, to that students, right? And what do you put there? You want to put a different kind of data, right? You don't want to put the same data, because if you put the same data, it's kind of like cheating, right? So, for example, if you, yeah, well, some teachers do that in a school, but normally when the school, yeah, some teachers they kind of mix and match. But I think a good understanding is no matter what problems you throw on that students, if the students really understand the concept, then it doesn't matter. He can, the students should be able to answer it, right? So you want to be able to throw a different set of problem. So to throw a different set of problem, you have to use a different set of data, right? So you call the val dash x, the validation data, right? And then after that, you got the prediction, and then you want to kind of to compare, right? So your students already um, got the test, and then now you want to see how good it is, the test. You want to compare it with the real answer. So you want to call. you want to call mean absolute error, and you put this two data, which is the test from the prediction from right, and then the real answer, and then you want to see how good they are, so you calculate it, and then you want to print out if you want to know, and then after that, using best value for max leaf nodes. So in this case, you are using 100 max leaf nodes, yeah, for decision tree. Because how do we know this? Because we already compute this at I think our previous um, session. We kind of like make like what if the max leaf node is 25? What if it's 50? What if it's 75? What is 100? 150 and 200? And it turns out the best um, kind model is the one that gives around 100, right? The best model, it means gives you the lowest mean absolute error, right? So, and then we want to train it again. We want to predict, and then we calculate the mean absolute error. And then this is just for the checking. So let's run this one. Let's run this one. I'm gonna just probably, yeah, make this slightly smaller, easier. I'm just gonna run this thing. Boom. Okay. So as you can see, the validation mean absolute error is 29,000 if you just don't choose any maximum leaf nodes. You leave it by default. If you choose kind of the best kind of leaf nodes, which is 100 in this case, right? And then you got a lower error, 27,000, right? So now we are going to use a random forest, which is basically a bunch of decision trees. Um, that's why it's called forest, right? Forest is basically a compilation of trees together. It's called forest. So we are going to call the random forest regressor. So we are going to point it. So right now we are going to set the model. So you're just gonna, I think you're just gonna random, just like this, forest regressor, and then random state. I use that random state equals one, and then you're gonna fit the model. So you're gonna um, so rf model dot fit, right? Um, so you are going to say fit train x, train y, train x, and train y, like that. Um, okay, that has to be capitalized. Train x and train y, and then you are going to mean absolute error. So you're gonna call the mean absolute error. Um, let me see. Mean absolute error. You need to predict first. Fit your model. Okay. File predictions, and then file y. calculate the minimum absolute on your random forest, on your validation data. Um, I think this doesn't work. Shouldn't work. Yeah. FR model is not defined. FR model. Oh, RF model. RF model. Trend Y is not defined. Um, ah, okay. Okay. 27,000. 27,208. So this is 27,282. Wait, why it doesn't? Mm, wait, I'm still confused. Why we didn't do the validation prediction again? Um, using the new model. I think you have to do this again, because now if you don't do that, you're still using the validation predictions from the old model. Yeah, so you have to, I think you have to do this. Like, I'll, I'll just, I'll just put it here. Okay. Yeah, I think you have to do this. Yeah, because you have to redo the whole thing, right? Because you're basically you are training using a new algorithm, right? Or a new model, and you already got the new model from here, and now you want to know how good is your model, so you want to use it to predict, to test the output, and after that you want to compare the output to the, yeah, because if you don't do this, basically you're using the old value from the old algorithm. Okay, I'm sure this is correct. So now, oh, I think there's something wrong. Wait, hold on. I, okay, I think I know where. I think this is the RF model. Yeah, yeah. There you go. Now it's 22,762. See? So it used to be 27,000. So it reduced significantly. Yeah, yeah. Let's see the solution, okay? Um, let's go to the solution. Model fit, RF, RF model, RF fault prediction. Yeah, RF file mean absolute error, RF file, validation Y. Yeah, it should be the same. Okay, I can do this. Okay, just to make it really, really sure, but it should be the same. It should be the same. 22,000. Okay, I'll run it again. Yeah, it's the same. Yeah, it's the same. Yeah, I don't know why it doesn't say correct. Strand X, strand X, strand Y, RF model dot predict, um, RF validation X, RF file prediction, yeah, RT val may, RF val may, mean absolute error. Yeah, yeah, it's correct. So, okay, so far you have followed specific instruction at this step. This helped learn key ideas and build your first model, but now you know enough to try things on your own. Machine learning competitions are a great way to try your own ideas and learn more as you invent machine learning, as you're ready for machine learning. Keep going. Okay. So, yeah, that's all, folks. You can see here, like, the improvement is quite significant, right? So over here, you are using just decision tree, right? And then you're trying to optimize it, trying to see the best decision tree, which is using leaf 100. It's still about, from 29 to 27. That's about roughly about 10% improvement, right? But if you use the XGBoost, sorry, random forest, the improvement is quite a lot, right? This is from like uh, 29 to 20,000. That's kind of like 30% improvement, probably, right? About 30%, yeah, 35%. So it's quite a lot. So, um, yeah, I hope this is useful for you. So let me know if you have any questions. I'll see you next time. We are trying to continue over here, I think, after what is, let's see, what is after the random forest. Um, oh, here is just the one I want to show you that, let's see if there's a one that's showing that is choosing maximum leaf is equals to 100. Uh, no, no, it's not here. I think it's the one that's on the exercise. Yeah. Anyway, so let's see. Yeah. So next time we're gonna continue. Oh, machine learning competitions. Okay, this is interesting. We're just gonna take a quick look. Oh, it's open a new exercise actually. Hmm. Okay, we're gonna do this next time. Machine learning competition. So, thank you for listening. Leave any questions, comments. Uh, keep on learning. Peace.